All right, let's practice drawing and naming some hydrocarbons. So we're going to practice drawing some bond lines. We're also going to practice naming and recognizing prefixes and so forth. So in these kind of simpler examples, notice here we can't do much. With methane, it's kind of just a dot because we can't draw a line that would represent two carbons, not one. Here we could draw a straight line representing two. Here we could represent three by going up, then down with a zigzag, and then for butane we could go up, down, and then back up, representing the number of carbons. So here we have one carbon, here we have 1, 2 carbons, 1, 2, 3 carbons, 1, 2, 3, and then 4 carbons. And that's the generic bond line kind of concept that we mentioned in that previous video. It's really just representing the carbon-to-carbon bonds. So here we have that carbon-carbon bond in the middle. Here we have this kind of zigzag here. And here we have this kind of zigzag pattern there for 4 that we're trying to illustrate with the bond line drawing. So we're going to practice both. Notice I do give away the 4 prefixes that have changed. Here we have a meth, eth, prop, and bute prefixes. This is replacing the mono, di, tri, and tetra prefixes that we used previously on exam 2. These are going to be changed forever for organic and exam 3. We'll give you an easier way to memorize them coming up. As we look at our 3 major hydrocarbon family classes, we have the alkanes. Remember, they have double plus 2 with their number of hydrogens. Alkenes are going to have double because they have double bonds. So they're doubling the number of hydrogens, losing 2 hydrogens because they now have that multiple bond that the alkanes did not have. Keeping in mind that alkanes are saturated, having those only single bonds compared to alkenes or alkynes, and then arenes being the most unsaturated of the bunch. We just don't name those in Introchem. Alkynes losing another 2 hydrogens. Notice out of the 3 carbon formulas, we see that kind of descending number from double plus 2, which is 8, to double, which is 6, to double minus 2, which is 4. That's because as we go to triple bonds, we're becoming more and more unsaturated. And that's the major difference between what we expect to see, because notice we've lost some hydrogens. We've lost hydrogens and now even lost more hydrogens, and that's what makes these family members very different. What's most different about them is their last 3 letters, ane versus een versus ein, and that's how we name them respectively. As we look at the top 10, we can see that we have the meth, eth, prop, and bute that's replacing the ones we saw before. So these are the 4 that are new. Those are the ones we'll have to kind of re-remember because they're changing. But then everything else from pent down to hept and then down to dec, that's kind of where we stop in Introchem. Those are really no different than what we use for inorganic or now organic chemistry. A fun way to remember this is to remember this sentence. Kind of creepy in a way, but usually the more random and the weirder the sentence is, it's easier to remember than the actual information. So if you remember, my evil parrot bites, that's enough to remember those top 4 that are new. And maybe that's all you need to remember for this test. But if you need help with that remaining group, then we can say, what does your evil parrot bite? Well, it bites puppies, it hexes hamsters, only near Delos. That gives you at least a clue to the first letter of each of those prefixes in order of the way we use them. So hopefully that'll help in your memorization of this as you use it in the homework and later on the test. As we start to name compounds, remember it all is based on chain length. So as we start to look at an example here, we see that it has 4 carbons. As it has 4 carbons, 1, 2, 3, 4, this is why they use bute in the name. Bute in the name. The difference being the way you number the double bond. So here we number it based on the shortest distance. So this would be a 1, or it could have been a 4 if we numbered from the right side. We just didn't because it would have been wrong. And then here it would have been just as easy to number it from the left side as the right side, because notice either way it would have been a 2 or a 2 depending on right or left. So in either case it's a 2. This one could have been a 1, but it could also have been a 3, because you could have numbered it 1, 2, 3. We just want to stay away from numbering from the long side. Sometimes coincidentally they can both be 2s, like is the other case. Also notice this is a alkene, and the reason it's an alkene is because it has a double bond. So because it has this double bond in the middle, or on the edge, so on the edge versus in the middle, this is why we add that ene ending instead of that ane or yne kind of ending for the other family members of alkanes and alkynes. So numbering is important. The reason numbering is important is because their physical properties change because of the location of their double bond, because that changes their overall shape, and therefore it can change their ability to interact with one another and their physical properties as a result. So remember to number from the short side. That's the most important feature, because in the homework you're going to have choices like A, B, C, and D. And both of these names look fine because it's 4 carbons long, it's a double bond, it's the third carbon from the right side, it's the first carbon from the left side. Both of those appear to be correct. The reason that we want to choose this one is because numbering from this side to the double bond is faster than numbering all the way through the chain just to get to the double bond from the longer wrong side. So always number from the short side, and these homework problems go pretty quick because most of this information, this butene part's probably there waiting for you. Most of these questions are probably going to be looking for, could you number it correctly? Not could you have the correct chain length, although there are some of those too. So how would we name something like this? There's no branches, so that makes it a little bit easier. One of the first things we want to do is count, so we can count left to right, but probably realize from the get-go that if we count from this right side, it's going to be a little bit faster. Let's go ahead and practice drawing the bond line. So as we go from 1, 2, 3, 4, 5, 6, 7, so 1, 2, 3, 4, 5, 6, 7. That's really the same structure, just simplified. It also has a double bond from the second to the right, so there's a double bond here. So those two structures are the same. The top one in red is just simplified, the bottom one is just the one from the textbook itself. As we counted that number, we should kind of get a handle on which side is faster. Well, if we number from this left side, it's 1, 2, 3, 4, 5 to the double, 6, 7. So again, that would be 1, 2, 3, 4, 5, 6, 7, and the bond line structure. Or we can number from the right side, and that would give us 1, 2, 3, 4, 5, 6, 7, which is the faster, means of getting to the double bond. So numbering from the blue numbers instead of from those red numbers would be the preferred answer. So in this case, carbon 2 is faster than getting to carbon 5. So that would give us a name of 2. 2 is the location of the double bond. And then because we have 7, we would use a prefix of hept for a heptagon. And then when we realize that there's a double bond, this double bond just says use the feature of double bonds, which is the last 3 letters, and that's ene. So 2-heptene in this case. So in a way, as we look at this name, because it'll probably be present in most homework kinds of questions, realize that the ene has to have a location, and that's the number. Numbers are always locations. Ene represents double bond, so it's basically saying look for the double bond to be on the second carbon of 7 carbons total. And that's an easy way to recognize and check some of your work. So 2-heptene. So 5-heptene is a choice. It's just a wrong choice because it's numbered from the long side, which is, in our case, the wrong side. As we start to throw in branches, just realize they use the same prefixes. So meth, eth, prop, and bute are the ones that are going to be most common to our Introchem semester, so they're just going to be reused. There is one that's kind of unique, and that's isopropyl. Meth is just one branch attached to many. Eth is 2 attached to many. Prop is 3 attached to many. But what's unique about isopropyl is it's 3 attached in the middle. So it's almost like the word iso for us means middle. So look for iso to be the middle of 3 carbons attached to a longer chain, just like we see it here. And it shows up a few times. You can imagine the most common version of this is isopropanol, which is rubbing alcohol. And that happens to be the case when this is an OH group. And we'll learn about alcohols a little bit later. So because it's somewhat common in the grocery stores and pharmacy stores, they do introduce it briefly in this chapter. Notice the only main difference when we add branches to parents is we change that YL ending. Kind of referenced that in that previous video, but we're changing the parent name of A and E to YL if we're attached to somebody larger than the 1, 2, or 3 carbons that we're attaching to the parent itself. And we're not really going to see branches longer than this in Introchem in the homework or the exam, although there are longer branches possible in upper level courses and so forth. So let's get back to an example. Here they tell us to name the branches, name the parents. The longest continuous chain is this one in kind of that light blue color. Notice when we number it, we have a choice from right or from left. So from the left, we would have 1, 2, 3, 4, 5. From the right, we'd have 1, 2, 3, 4. So to keep it somewhat clean, I'm going to go ahead and number it from the faster side. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 tells us non. So that 9 carbon length gives us that non prefix. The fact that we see all single bonds, no doubles, no triples, tells us that ane is all single bonds. And that's the kind of parent suffix for the alkane family. We do see a branch. The first branch is located here. It's on number 4 carbon, and it's only 1 carbon long. So because it's located at carbon 4, we say 4. And because it is 1 carbon in length, we use the prefix meth. But because it's not a parent, we don't say methane, we say methyl. Very similar with eth, with 2 carbons next door. Here we have 2 carbons at carbon 5. So 5 is the location. Numbers are always locations. And then words represent length. In this case, 2 is eth. If it were a parent, that would be ethane. But since it's attached to 9 carbons, which is a whole lot longer, we say ethyl. And then to put this together, what we do is we realize alphabetical order is still important. So here we have an E before an M, and then our parent goes last. So 5-ethyl, 4-methyl, nonane, all crammed together. So alphabetical order will be important if we have more than one branch, and that would organize them based on E versus M in this case. What would happen if we had 2 of the same group instead of one that was different? Well, if we no longer have an ethyl group, we no longer have to worry about alphabetical order. But if we have 2 groups that are the same, both of these groups having 1 carbon, located at carbon 4 and carbon 5, so carbon 4, carbon 5. 2 groups says di. 3 of the same groups would be tri, 4 of the same groups would be tetra. So we do use those prefixes when there's a multiple common branch, as is the case here. So di really just says look for this group 2 times. Methyl says it's a 1 carbon length group. And non says you're 9 carbons long. Ane says you're all single bonds. And that's how we get clues to know right from wrong answers. Remember, these numbers over here, numbers are locations. Words like meth and non, those represent length. So try not to confuse numbers from prefixes, because that's the easiest way to get wrong answers. Let's try a couple here. We have 3 across, 1 up, 1 down. So let's do some bond line practice on these just for fun. So 1, 2, 3 across. We have a branch both in the middle. So that's the best interpretation of bond angles and so forth. We could draw wedges and dashes and make it even more so, but that's basically the same structure. Here we have kind of 5 across, so 1, 2, 3, 4, 5. On the second carbon to the right side, we have a branch of 1, but we also have a branch of 2. So those structures are the same. Now it's a matter of naming and understanding the parent chain first. So here the parent chain is definitely the 3 in the middle. So 3 carbons tells us prop. Once we realize that they're all single bonds, we can say propane. Here we might have 5 across, but that's not as long as the 4 across and the 2 down. So here it's actually the parent that goes this way that matters. So it doesn't have to be the prettiest straight across chain. It has to be the one that is the longest without going backwards. So once we see that this has 4 down, 4 across and then 2 down, that's 6 total. So 6 carbons would be a hex. All single bonds is an ane. So there's the parent. Then we have branches. Notice in these branches we have 2 of the same branch. We have this branch being like this branch. That would be a di group. Just like over here we have 2 of the same. That would be a di group. Then we realize that they're only 1 carbon long, so we use dimeth. Dimeth. And then we realize that they're attached to something longer, so dimethyl. Dimethyl. So both of these are dimethyl, in this case propane, or a dimethyl hexane. What's different though is length. In this case, distance to those branches. So in this case, we could have a 1, 2, 3, or from the opposite side, 1, 2, 3. So in this case, it doesn't really matter at all. It's carbon 2 that matters. So that's a 2 and a 2 dimethyl. So we need 2 numbers because each one represents one of them's at 2 and then the other one's at 2. Carbon 2 specifically. From the left side, we have 1, 2, 3, 4. From the bottom side, we have 1, 2, 3. 1, 2, 3 is faster. So in this case, 3 is the number we need. So that's a 3 and a 3. It seems redundant, but it's because we had 6 choices. This is saying specifically one branch is at 3, and so is the other. So it's just a coincidence, but we need a number for each group. So those are locations. Everything else is length. And that'll help us better understand some of the homework. As we look at this example here, going a little bit faster just to save a little bit of time because this starts to get a little bit tedious. It's just different examples with different lengths in the end. Here we have 6. They numbered it for us, which is nice. 6 tells us hex. As soon as we realize that there's the maximum number of hydrogens, there is no doubles or triples, we can still say ane. If there was a double, we'd say ene. Triple, we'd say ine. And then from that 6, now we have 3 branches that are the same. Anytime that we have 3 branches that are the same, we would say tri, because there are 3 repeating identical groups, identical branches. They're all 1 carbon long, so we say meth. They're attached to somebody bigger, which is the 6 total, which is methyl. Methane would be the parent of CH4. Methyl would be just a CH3 group attached to something larger, in this case a larger 6. But notice we have 3 identical groups, so we need 3 location numbers. This one's located at carbon 2, this one's located at carbon 4, and the other one also located at carbon 4. So notice numbers are for locations. Everything else is length. This just means 3 times. Here are meth is 1 carbon, and then here are hex is 6 carbons. Again, A meaning all single bonds. Those are the clues to look for because these answers are going to be there for you. You're not creating them in the homework or on the exam. You're making sure that they are the right length, the right functional group, the right hydrocarbon group, and then the right position, the right location of the actual group on that chain. Unfortunately, when we have a double bond, we have to use it in the longest parent chain, even if it's not the longest overall. So what we're seeing with this example here is that even though there's 9 across, it's the 8 that contain the double that actually matters, because it contains both sides of this double bond. Then we use the locations here of, we have a 2 carbon branch. 2 carbon branch is ethyl. Here we have 2 identical branches of 3. So here's the 2 times. This is the 3 carbon propyl. And then located numerically at carbon 1 is a whole lot better than at carbon 7. So we use that 1 here to locate the position of the ene, which is the double bond. And then we also represent that of that parent, 1, 2, 3, 4, 5, 6, 7, 8 is the actual parent oct. So again, eth is 2 carbons located at carbon 2 of the 8. Propyl is 3 carbons located at carbon 5 and at carbon 4 of the 8. Di just tells you that there's 2 of them. It's kind of redundant to have di and the 2 numbers, granted, but that's what they chose to do. And everything else is just chain length. So looking at this example, we need to make sure that our longest parent chain happens to be in that group, and notice that it is here with the 6. So anytime we have 6, we would say hex. Because we have a double bond, now we would say ene. Because there's a double bond, we have to number shortest to it first, and then wherever the chips may fall for other groups, they happen to be wherever they are. So the hierarchy is number to the double triple bonds first. So numbering 1, 2 is a whole lot better than numbering 1, 2, 3, 4 from the other side. So that 2 is the location of the double bond here, and that's where we say 2 hexene. Then we realize that we have these 3 branches that are all the same. This branch is the same as this branch is the same as this branch. So anytime we have 3 of the same, we would say tri. We realize their length is only 1, so we say meth, and then attached to somebody bigger is YL. And then we just need numbers to represent locations. The first location is carbon 3, and then we have 2 at 5. And there's the name we look for. So again, locations, length would be 1 carbon branches, 6 carbon parent, double bond located at 2. And then these 1 carbons are located at 3, located at 5, and located again at 5. So it's all about recognizing length and location. One last one. This one's a little bit unique because it has a triple. So just for fun, I'm going to draw its bond line structure because it would be different. A lot of students would probably draw this. And then part of me dies on the inside when you draw these double and triple bonds, and that's no way near 180 degrees. So with triple bonds, you need them linear. So out linear, and then you can draw your branches. So be careful. Avoid bond angles and bond line drawings that don't match up. For this one, we do have 4 total carbons. So 4 total carbons would be bute. The fact that we have a triple bond says butene. And the location could have been 1 from the right or 3 from the left. Both will be choices in the homework. But what's important is we always choose the fastest numbering sequence, which is this carbon here, and that's carbon 1. So that's a 1-butene. So 1 tells you the location of this triple bond. And then of the parent, which is this one here, we do have a branch. That branch is only 1 carbon. It's located at carbon number 3. So it's located at 3, but it's only 1 carbon long, so 3-methyl. Notice the location of the triple bond determined its location. So the location of multiple bonds is always looked at first. And that's kind of a crash course in naming hydrocarbons. Again, we're never going to be naming them from scratch. We're going to be naming them with choices, and that makes it a little bit easier, as long as you know your prefixes and you can count from the shortest side. Catch you next time.